So here's the big idea. We will be given a rate of change of one thing, and then try to find the rate of change of another thing. And this is going to bring back our implicit differentiation and our chain rule idea to figure this out. So you drop, okay? You drop a pebble into a lake, and you look at the shape that it makes. And you're like, oh, it's a perfect circle. So you try to drop a brick and think, will it make a perfect rectangle? You're like, no. Kind of makes a circle again. So when you drop something into water, it makes a ripple, which makes the circle go out, and usually the speed at which the circle is moving out is the same. So here we have a question saying, if the radius is increasing at 2 meters per minute, how fast is that circle increasing at that time? In other words, right, here, if we waited 1 more minute, we would expect the radius to increase by another 2 centimeters. That rate is really obvious. But if we waited 1 more minute, how much will the area increase by at that time? So the way that we go about these questions is we have a formula. Our area of our circle formula is pi r squared. And in a related rate question, they're going to give us some rates. In other words, we are told that dr dt in this case is 2 meters per minute. Which means that radius is a function of time. If we have a dr dt, that means there is some equation, even though we don't know it, that is radius equals blah, 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 time. Its derivative happens to be 2 meters per minute. We are asked to find dA dt equals what at 100 meters. Notice we have no variable t anywhere. Okay? But we're told dr dt, and we're asked to find dA dt, and we don't have any equations with t. All we have is an equation that relates our area to our radius. And this is where implicit differentiation comes in. We take the formula that we have, and we take the derivative with respect to t of this whole thing. Even though we don't know, right, we don't know what a of t equals, and we don't know what r of t equals, we're going to imagine they exist. And implicit differentiation allows us to do this. What's the derivative of just a? Well, it would be 1 times by implicit differentiation. We'll say, well, the derivative of a is just derivative of a. It'll be dA dt. How do we do the derivative of pi r squared? Well, you would bring the 2 out in front and get 2 pi r. And then because you're doing with respect to t in implicit differentiation, every time you have a variable, you're going to have to do dr dt. what do we want to find? This is what we're trying to find. And I can write in here, we're trying to find dA dt when r is 100. Do I have all of the information now that I could plug in? Well, I want to find it at 100. Do I know dr dt? Yes, that was given to us to be 2. And I multiply this all out. This will be 400 pi. And area is measured, what's our unit here? In meters. So area is meters squared. Time is in minutes. Okay. So we were just dropping a pebble into the water. More devastating effects of thinking about this is in war, when they drop a bomb, it goes out in a circle. So what they can figure out from things like this is what is the damage increasing by at a certain time? How much more area gets destroyed? And so that's a negative outlook on this same question, but an important thing to know. If something's going to happen, what kind of damage, what kind of time do people have to get out of that damage rate? Because the explosion is spreading out at a constant rate for the most part. But the damage is increasing so much more every moment. Like right here, 400 pi meters squared. That's like 1,200 meters squared. That's huge as of amount of devastation that would happen in the next minute. Okay. These are related rate problems. What they're going to do is you will always be asked in a related rate problem something in regards to time. Usually it's like this is increasing at this speed, so it's meters per second. Or, yeah, in this case, the radius was changing at meters per minute. We want to find out how fast is the area changing. It's also per time. But we do not have these equations. We don't even know what they look like. This is exactly what implicit differentiation does. It allows you to do math with equations you don't know or can't figure out. Okay? And it allows you to take the derivative, even though I'm taking the derivative with t, but there are no t's. Okay? But it changes if there's no t's in the final equation either. Now there's just the derivative of a, the derivative of r appears because of implicit differentiation. Again, we don't know what those equations are, but we know what the value of dr dt is. We're trying to find it specifically when r is 100, so now we can plug in something for r, and we can solve this. Okay? Sometimes these equations will also have an a. Let's say you had some formula that was a squared, right? When r is 100, you could figure out that a was, plug it into this formula, you know what a is when r is 100. So you could plug in the values even though you don't know t, which is what makes our implicit differentiation help us with our related rates. And I think if you understand this idea, because often students find related rate problems one of the hardest problems of first year calculus, I'm hoping that you'll be like, oh, it's not so bad. That all we're doing is writing out what we know. This is a very important step. Then doing the implicit differentiation, and then plugging in what you already knew will get you the answer to solve. So what we're going to look at tomorrow is more related rate problems in different situations. Some of them are a little bit complicated to set up the equations, so we'll practice that.